Swayam Prabha. Digital India. Educated India.
So suppose I have a 2 by 2 matrix and this is the T12. That means I interchange the first row and second row. This is my T12. Okay. What is the action of T12 on E1? Yeah, that is the first column. Action of T12 on E2. This is the second column. So this is E1, this is E2, and this is E1. So if this matrix is obtained by interchanging the first row with the second row, then you see that E1 is mapping to E2 under the action of T12, and E2 is mapping to E1 under the action of T12. So E1 and E2 are being interchanged by the action of T12. Okay. So if I take T12 and multiply by any matrix, okay, what happens? This is equal to 0, 1, 1, 0, A, B, C, D. So use matrix multiplication, and so 0, 1 times AC is C, 0, 1 times BD is D, and 1, 0 times AC is A, and 1, 0 times BD is B. So you see that the first row was AB, and that has been transposed here, and the second row CD has been moved to the first row. So T12, when it is acting on a 2 by 2 matrix, it is interchanging the first row and second row, and this is also true in general. So if I take Tij and multiply Tij with A, so Tij is a n by n matrix. So in order to multiply this matrix, A must be an n by m matrix. So this matrix is obtained from A simply by interchanging ith row and jth row. So this becomes jth row and this becomes ith row, and other rows become the same. So Tij is obtained from A simply by interchanging ith row of A with the jth row of A. Okay, that is the action. Yeah. So if I multiply Tij with Tij itself, what happens? I will get identity, because Tij acting on Tij will interchange the ith row and jth column of Tij. So I will get back the identity matrix again. Yeah. Okay. So this says that Tij is its own inverse. So it's an invertible matrix. Yeah. This Tij is invertible matrix. Tij times A is the matrix obtained from A by interchanging ith row and jth row of A. Okay. So therefore, if I operate Tij, multiply Tij with Tij, I will get identity matrix, and therefore Tij is invertible, and it's its own inverse. This should be I here. Yeah. Okay. So Tij is invertible matrix. It is its own inverse because Tij square turned out to be identity. Now let's look at second type. The matrix obtained from identity matrix adding m times Ri to Rj. Okay, that is called Tij_m. So Tij was the matrix obtained from identity matrix by interchanging ith row and jth row, but Tij_m means that I am multiplying ith row by m and adding to the jth row. So then I get this Tij_m matrix. Okay, and the action of Tij on m, on a arbitrary matrix, is again easy to understand. In the way we did this for T12, we can see what is the action of Tij on a given matrix. So if I multiply Tij m on a matrix, this is the matrix obtained from A by adding m times ith row to jth row. Yeah, that is the action of Tijm. So therefore, if I take Tijm and then take Tij minus m, okay, this will be identity. Because I am reversing the operation. So this shows that Tijm is invertible. This is invertible. For any m could be 0 also. So Tij 0 is just the identity matrix. Okay. So this is the second type of elementary matrix, which is obtained by adding m times ith row to the jth row of identity matrix, and I get this Tijm. Okay. So this is called an elementary matrix of type 2, and as I wrote, the Tijm times Tij minus m is identity. So inverse of Tijm equal to Tij minus m. Right? This is the second type of elementary matrix. Let's look at the third type of elementary matrix. This is obtained from identity by the elementary row operation m times Ri, where m is not equal to 0. Okay, m is not equal to 0 here. Okay, and this is an invertible matrix. What is the inverse? It's a diagonal matrix, and we know that if I have a diagonal matrix, then to find the inverse, we simply multiply this by the matrix where ith row has 1 over m in it. So Tim times Ti 1 over m. That will be identity. So therefore, Tim is invertible, and Tim inverse equal to Ti 1 over m, because m is not equal to 0. This is the third type of elementary matrix. So Tim is called elementary matrix of type 3, and its inverse is Ti of 1 over m. Okay, yeah. So I described three matrices which are called elementary matrices, and I'll repeat. The first type was interchanging ith row with the jth row. So take identity matrix, interchange ith row with jth row, I get the elementary matrix of first type. Elementary matrix of second type, I add a multiple of ith row to the jth row of identity matrix. That is the second type of identity matrix. The third type of identity matrix is I multiply a row by a non-zero scalar m. That is Tim. Okay? And all these three matrices are invertible. Now here is a theorem. An elementary matrix is invertible, therefore, and the inverse is also an elementary matrix of the same type. Yeah, Tim inverse was Ti of 1 over m. So it is an elementary matrix of same type. Ti, then Tij. Okay, Tij, inverse of Tij was Tij itself. So that was an elementary matrix of the same type. And then we proved that the second elementary matrix Tijm, yeah, its inverse is Tij minus m. So that is again an elementary matrix of the same type where m is replaced by minus m. So every elementary matrix has an inverse. The inverse is a elementary matrix of the same type. Okay, the parameter changes. M changes to minus m if it is the second elementary matrix, and m changes to 1 over m if it is third elementary matrix. Okay. Yeah. So this we have proved that an elementary matrix is invertible, and the inverse is also an elementary matrix of the same type. Okay. Now let's prove a very interesting characterization of what are the building blocks of elementary of invertible matrices. So let A be a square matrix. Then the following are equivalent. A can be reduced to identity matrix by a sequence of elementary row operations. Now this fact says that the row canonical form of A is the identity matrix. We observed, I didn't prove this, but you can read the proof, that row canonical form of any matrix is unique. So if I can reduce a matrix, square matrix, by elementary row operations to identity matrix, then identity matrix is the row canonical form. Okay, so this statement says that the row canonical form of matrix, the square matrix, is identity matrix, which means that by a sequence of elementary row operations, I can change A to identity matrix. That is the first statement. This statement is equivalent to A is a product of elementary matrices. Yeah, A is a product of elementary matrices. Then A is invertible. This is equivalent to A is invertible. Okay, and fourth statement is Ax equal to 0 has only trivial solution. Ax equal to 0 has only the trivial solution. So these four statements are characterizations of elementary matrices. Okay. A can be reduced to identity by a sequence of elementary row operations. That means the row canonical form of A is identity matrix. Second statement is A is a product of elementary matrices. So this means that invertible matrices are built out of elementary matrices, in the sense that the only way to get invertible matrices is by multiplying certain number of elementary matrices. Yeah. The last statement has to do with the nature of solutions of a homogeneous system of linear equations. So if A is a square matrix and Ax equal to 0 has only trivial solution, then we can say A is invertible matrix, and vice versa. Okay. Yeah. So these four statements are equal. Let us give a proof. So when I say that four statements are equivalent, I need to show that they are equivalent to each other. That means any statement is equivalent to any other statement. But we prove this by proving that the first statement implies the second statement implies the third implies the fourth, and fourth implies the one. And that will prove that all the four statements are equivalent. So let us prove that if identity matrix is the row canonical form of A, then A is a product of elementary matrices. Okay. So what is the meaning? How do we obtain row canonical form? We simply by performing elementary row operations. Okay. So if I apply an elementary row operation, on A, and I get the matrix A1. Okay. Then A1 is obtained by multiplying an elementary matrix on the left to A. Right? There are three types of row operations, and I showed you that they all can be affected by pre-multiplying A on the left by an elementary matrix. So if I perform an elementary row operation, then and I get A1, then A1 is simply product of an elementary matrix time and A. I do another elementary row operation. That means I pre-multiplying E2 with A1, and I get A2. But this is equal to E2 E1 A. Okay, and so on. Finally, I get I, the identity matrix. So it's clear that this identity matrix is obtained by multiplying A on the left by a certain number of elementary matrices. Okay. Now this equation says that A is invertible. Why is this so? Because I know the inverses of elementary matrices. So I simply multiply by their inverses. So suppose let us take a simple case: E2, E1, E2, E3, E3, E2, E1, A equal to identity. And I want to find the inverse of A. Yeah. So multiply by inverse of E3. Then multiply by inverse of E2. Then multiply by inverse of E1. So I have to do the same thing here. So E1 inverse, E2 inverse, E3 inverse. This becomes identity, and therefore A equal to E1 inverse, E2 inverse, and A3 inverse. So A has become a product of elementary matrices. Yeah, that's what it says. That if the elementary row operations which are used to get identity matrix from A, then A becomes a product of elementary inverses of the elementary matrices of the same type. So in this Gauss elimination method, to get the row canonical form, yeah, of A, if A is invertible, then it says that identity matrix is the row canonical form. Yeah, and this says that A is a product of the inverses of the elementary matrices which were used to perform the elementary row operations on A. So we have proved A is a product of elementary matrices. If the canonical row canonical form of A is identity matrix, then A is a product of elementary matrices. Now, once A is a product of elementary matrices, then it is invertible, because we showed that inverse of invertible, the product of invertible matrices is invertible. Therefore, A is invertible. Yeah. Then C implies D. If A is invertible, and then AX equal to 0. If I have AX equal to 0 and A is invertible, I just multiply by A inverse. Yeah. And this is equal to 0. And therefore, X must be 0, because this is identity. So AX equal to 0 will have only a trivial solution. So C implies D. That is all right. Now let's prove D implies A. Okay. So we are assuming that I have a system of n linear equations in n unknowns, and it's a homogeneous system of linear equation, and it has only a trivial solution, namely X equal to 0. Yeah. Then I want to prove that A can be reduced to identity matrix by a sequence of elementary row operations. So one statement is about solvability of a homogeneous system of equations, which says that there is a unique solution, namely the zero solution. The second fact is about the row canonical form. Yeah? That the row canonical form of A must be identity matrix. Okay. So yeah. So in order to prove this, we first observe that a square matrix is in row canonical form is either the identity matrix or its bottom row is 0. The row, if a matrix is in row canonical form, then the 0 rows must occur at the bottom. Yeah. So if the row canonical form is not the identity matrix, then there must be a 0 row at the bottom. Yeah. So square matrix in row canonical form is either the identity matrix, or because above every pivot and below that pivot, all the entries are 0. So imagine I have a square matrix and it is in row canonical form. Yeah? Then the number of pivots, if it is n by n matrix, the number of pivots is either n or it is less than n. Suppose it is equal to n. That means every column has to have a pivot. But the pivots are sliding from left to right as you go from one column to another. And therefore, if there are n pivots, this matrix has to be identity matrix. If there are less than n pivots, that means the number of non-zero rows is less than n, and therefore the bottom row must be equal to 0. Okay. That's what it says. That if I have square matrix, then the row canonical form has these two possibilities. Either it is identity matrix or the bottom row is 0. Okay. So suppose, so I want to prove that if Ax equal to 0 has only trivial solution, then A can be reduced to identity matrix by a sequence of elementary row operations. So suppose, assume to the contrary, that A cannot be reduced to identity matrix by elementary row operations. If A can't be reduced to identity matrix by elementary row operations, then the row canonical form must have 0 row at the bottom. Yeah, it must have 0 row. So there is a 0 row here. And there are other entries. This is my row canonical form. But when I take the row canonical form and set up the system of linear equation, this system and Ax equal to 0, they have same set of solutions. They will have same set of solutions. But now let us understand whether A prime x Okay, A prime x equal to 0. That means the bottom row is 0. So number of pivotal variables is less than n. So there is a free variable. Yeah? There is a free variable. Once there is a free variable, there are infinitely many solutions. So we have arrived at a contradiction. Our assumption was Ax equal to 0 has only the trivial solution. But if A can't be reduced to identity matrix by elementary row operations, then its row canonical form must have 0 row at the bottom. Once it has 0 row at the bottom, there are fewer than n pivotal variables. So there is a free variable. Once there is a free variable, then A prime x equal to 0 has a non-trivial solution. That is a contradiction. Okay. So any questions on this? Is a tricky proof. Any questions on this proof? All right. Okay. So this theorem actually leads to a algorithm to find inverse of a matrix. So far, we don't know how to find inverse of a matrix. Yeah. So let us see that this gives an algorithm to find inverse of a matrix. And linear algebra is about algorithms for linear equations. We have to find, we know Gauss elimination method. That's an efficient method to solve system of linear equations. And then we are introduced to finding inverse of a matrix. So if Ax equal to B is our system of linear equations, and A is invertible. Yeah. If my system of linear equations is this, and A is n by n, and A is invertible, then if I had access to A inverse, I just multiply. And that says that A inverse B, that says that X is equal to A inverse B. So in one shot, I find all the solutions. Okay. If A was invertible, and I have access to A inverse, then I can find the solutions if it is n variables and n equations. Okay. So it's important to have access to inverse of a matrix when I have a system of linear equations. If we have an efficient algorithm to find inverse, then we will have efficient algorithm to find solutions of a system of equations also. Okay. So here is a consequence. Suppose I have n by n matrix, and B, there is a B, so that BA is identity or AB is identity. Then A is invertible and A inverse is equal to B. Remember, we had in the definition of invertible matrix, we had imposed that there's a matrix B, so that AB is identity and BA is also identity. But now we are saying that only one of these conditions has to be satisfied for a matrix to be invertible. Okay, right? So let us prove that if it is enough to prove one of the equations, BA is identity or AB is identity. Okay. If AB is invertible, then A and B are both invertible. If the product is invertible, we proved that if A and B are invertible, the product is invertible. But now we are saying that if A times B is invertible, then both A and B are invertible. So let's prove that once I have one equation, BA equal to identity, then for any x, BAx is x. Yeah, because BA is identity. So BAx must be equal to x. Yeah. So if how to prove that a matrix is invertible, we just check that Ax equal to 0 has a trivial solution. So suppose Ax equal to 0. So suppose C is the inverse. Then C is equal to BA times C, and that is BAC, and that is equal to, so B is the inverse. Okay. Yeah. If AB is invertible, then its inverse is D. Then ABD is equal to ABD equal to identity, and therefore A is invertible, and so B is also invertible. Yeah. So once product is invertible, the factors are also invertible. Okay. Suppose I have a square matrix and this is invertible. In order to solve this system Ax is equal to B, we transform the augmented matrix into IC by elementary row operations. Once A is invertible, then I showed that its row canonical form is identity matrix. So when I convert A into identity matrix, I get a augmented matrix IC. Okay, IC. So Ax equal to B if and only if Ix equal to C. And so for every X, yeah, every X, therefore AC equal to B. Yeah, right. So therefore C is the unique solution of Ax equal to B, as I explained earlier. So this observation is the basis of important method to find inverse of a square matrix. So I think our time is over, and we will continue. There are the last topic in this chapter is finding algorithm of for inverse of a matrix, which is called Gauss-Jordan method. I will cover this next time on Wednesday, and then begin with the next topic of determinants of matrices. Okay, so thank you all.